On to our second speaker of this session, Technologies for Transformation. I'm really happy to welcome Bejoy Jose, who's with the Yokogawa Engineering Asia here in Singapore. And Bejoy is the Vice President, Product Strategic Business Unit and Life Innovation Business. He has the longest job title of everyone today. So Bejoy, please come to the stage and let's see your presentation. Thank you.
Thank you, Bob. We've been discussing OPA for quite a long time. And a very crude takeaway from OPA is don't get stuck to a source. Let me move away from the podium now. I'm going to be talking about, to set the perspective, I'm going to be discussing about the level 1. Right? And this is where all the action is, the source of all the data. Maintaining this data reliably is very critical. Maintaining this data is the key for anything that goes above this, right? And when I see around, I can see quite a lot of you who would have dirtied your hands as you work on with this in the early part of your career. And by that, I can see quite a few of you smiling, a clear indication of how some of us have learned doing things with the hands. It was then, dirtying with the hands was a kind of satisfaction, or we would have job satisfaction when you troubleshoot and run the show better. But now the point is this, is that still the best way? Do you think the current generation or the current people are interested to dirty the hand? Or the point, I don't mean the next generation. I would rephrase this question, is when there is opportunity with AI and digitalization, should you really get back, dirty your hands, or work smartly? And this is what I'm going to be focusing on. We run back a little into the history, touch upon some of the traditional practices. The traditional practices are not rocket sciences, but these are things what all of us have been following over the years. But doing it right is most important. Recording that is most important. And then we see how we're going to be leveraging this data. Well, this is another version of the last slide from you, moving on from pneumatic to analog to digital, whether to the sensing or communication and the maintenance, right? The tools, whether it was screwdrivers and spanners before, move on to multimeters, analog multimeters. Anyone here remembering the analog multimeters? I should also put up my hands. Right? We move on from that into the digital multimeters. And then came the age of digital communicators. And then we moved on to tablets. And now we speak of IR, AR, VR, XR, a few more of these Rs, and all these wearable devices which assist in effective maintenance. Now, a lot of these devices are already giving a lot of information, right? A lot of diagnostics, like the case of pressure instruments, for instance. These can do an impulse line detecting. It was in place for over 20 years. Also, the device can detect which side of the line was blocked, or detecting water in the wiring terminal. It was quite normal, because these really impact the performance. Looking at level instruments, the frequency variation kind of issues were easily identifiable. Looking on the Coriolis, monitoring the tube thickness or the tube stiffness, or built-in verification for the flow meters. Looking on the analyzers, electrode deposition monitoring stuff on the liquid analyzers, GC with AI come in for doing the maintenance. So here we have a lot of these devices with a lot of data, right? And the question is, with these diagnostics coming out of the data, do we really have to do periodic routine maintenances? Can we optimize the way we maintain? And at the same time, we also look at periodic calibrations and how we're going to be optimizing on these. I could find this old data, which was published quite some time back, but it makes sense about equipment failures. And I would just correlate this exactly into the instrument failures. Failures, as all of us know, is from hardware, human issues, or external factors. Drilling down from that would be equipment issues, maintenance-related issues, or process faults, process upsets, or simply the way it was handled. Now, we would be able to address almost like 65 to 70% of these root causes through predictive diagnosis, integrated maintenance practices. Now, when we see the common failures of instruments, these can be because of process-related areas, right? Impulse line clogging, scaling, corrosion, pitting, or it can be because of environmental factors, because of high humidity, lightning, right? Ambient temperature variations. And aging of components is another factor as well that contribute to the deterioration of the devices. Oops, that is a little noisy. Yeah, it's stable here. Right, and when I move on to the next stage, it's the traditional practices, how we've been maintaining once the instrument is back on the lab or in the plant itself. Very fundamental aspects about visual inspections, functional or electrical inspections, and capturing the diagnostic informations. So when we go on to visual, what is checked is, for instance, the condition of the wiring terminals, condition of the electrical sealing, the glands, the PCBs, the sensing diaphragms, or for instance, the housing of the instrument. If you see, for example, the instrument on the top right, it is giving a very stable 40-20 milliampere. So for somebody who's sitting in a control room, it has been a very stable instrument. But once they see this one, will anybody ever dare to put it back in operation? I can see the smile, right? Nobody's going to do that. But this is where the importance of capturing visuals and images comes into picture. So these need not be done by very specific inspection activities. These can be done either during the routine calibrations or during a proof test. Maybe there are different forms of capturing these informations. In the past, it could be a checklist, tick it up. A little bit more digitalized is an Excel sheet or a tablet into which we key in. And now it's possible also to get images out of this. And the point is how we would utilize these data from the previous rounds of maintenance to predict the future. Moving on, the electrical functions, right? This is another data that is available. Comparing between the analog and digital signals of the devices. Are those exactly the same? Looking at the insulation resistance factors or anything to do with the variation on the calibrations. These are, again, a lot of information that is available and that are captured during subsequent maintenance activities. And the key point is how you utilize the data from the previous years. Do we want to keep doing what we did in the past, repeat the same thing every other day, or from these we learn and optimize and redo things? Again, we discuss about the diagnostics. There are a lot of diagnostic information available on the devices. Log in using any of the asset management systems, a lot of data. The point is, again, how do we make better use of these available informations? And as part of traditional maintenance practices, we could have, as I mentioned, some checklists where the technician goes check, 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 check. Many checks are so automatic that the check comes in without actually the testing done. The checking is very fast. Now, we have all these kind of data. By the proof test, as per the IEC 61511, we also need to document what we do it, right? So then, for that purpose, again, these documents help. Here, what we're trying to see is how we would utilize all these documents into the system, integrate these informations to do a prediction of planning of what kind of devices can be reused or what can be replaced. Now, going on to calibration and optimization. Over the years, stability of, I'm going to take an example of pressure instruments. When I started my career, 6 months of stability was something great. Please don't calculate my age by the specifications. Right? And today, the fact is, we are speaking of even lifetime stability by some of the people. Now, the point is, what are we doing out of this improved stabilities? Coincidentally, this morning, I got a feeder from ARC, and this was the most recent pressure transmitter market report. Right? Being in this business, I'm always interested to see what's my share of business. But what was more interesting was the statement along the pressure transmitter maintenance considerations. It's important. I'm going to quote a few words. I would slip a bit, but continue the rest. It's important to know how often the transmitters will need calibration and what will be involved in doing that. This is one part of the topic. And later on, it says, some transmitters can now offer longer stability specifications, thus reducing maintenance cost. In some applications, they require fewer calibrations. I'm really happy to see this. I've been shouting this from top of my voice for donkey number of years. And every time the question is, how do I validate this? And I believe this report from ARC also helps a lot in the mindset change, right? And this is exactly what was captured. I put up this slide before I read your report, right? And this has been the practice that some of the customers have been following as well. Traditionally, critical tags are calibrated more frequently, non-critical ones less, and the ones on the offsite, the poor ones, nobody care about. And this data, by standard, is available in every office. It could be as physical papers, or in the CMMS system, or any other platform. The question is, what are we doing with these previous data, right? Every time a calibration is done, the in and out data is available. So when you record this data, and we find that the incoming and the outgoing information, or the incoming from the past outgoing has not changed, this sets a basis to rewrite the calibration specifications. Many times when we speak out, the first question comes up is ISO says we should do a calibration. But the point is ISO does not say how frequently you should calibrate. It just defines when you need to write when you should calibrate. That's all. So we just need to rewrite our SOPs. And these are all the traditional methodologies, but there are still a lot of room, ample space for us in the traditional methods to still optimize and improve. Verifications is not just on transmitters. Now look at the flow meters. All of them have online verifications. This is also possible to stretch the interval between calibrations. Obviously, on the custody loops, it's a no-go. You still have to calibrate. But how many of them are custody loops? A lot of them in the other applications. These can also be used. Looking at GC, we have AI-based diagnostics, which can also predict the condition of the columns. In GC, the column is one of the part. Age of column is something critical. So with the AI built in of the diagnostics platforms, we are also able to predict when the column needs to be replaced. So the crux is that with the data that's available today in its crude manual form, we can still optimize. And once we move all this data upwards, then comes the opportunity for us to really get guided, optimized maintenances. So by traditional practices of visual inspections, we have data from Excel sheets, checkpoints, images. We look at electrical informations, which is pulled up from the devices. We look up at diagnostic functions. The point is here we have a whole lot of data. And with this data, we are able to do a meaningful representation of information that is available, right? You can create dashboards, informations of which make meaningful sense, know the device information and the statuses. And further on, I also learned a very new terminology today that was about agentic AI, right? So we use agentic AI, though I didn't know what it was until before attending this session. We are able to go into predictions, right? The data are available. Like, for instance, in case of a Coriolis meter, it's not so easy to pull out and do a lot of maintenance. It's online. So monitoring the stiffness of the tube and having a trend of how the stiffness is varying over time, integrate with AI, gives a prediction as to when is the likely time this particular meter is going to have a problem. That's giving ample space for early informations. We could compile a whole lot of this data, go into the calibration domain. We have the data from the previous years of calibrations, utilize these to a prediction as to how we are going to optimize these calibrations. And also by the process trends and the reading drifts, here again we are able to predict when is the right time to do the next calibration, or when is the right time to do the replacement of these devices. Imaging AI also comes into picture because we would correlate all the parameters what we saw before. Visual parameters, the electrical parameters, the diagnostic informations. And out of these, we get meaningful informations by which we can decide who will do what, when, and how to optimize what we have been doing. And with this, we are focusing to the 3 key goals that Yokogawa is focused on: well-being, circular economy, and net zero. And if you see all the practices that has been discussed today, it's focused on improving efficiency in the society and industry, optimizing the life cycle of the plant, improving health and safety of the people around, creating a resourceful, that's basically having a better recycling, maximizing life, and creating a workplace where maximum amount of the people can be taken and have a satisfaction of those who are doing things. In a nutshell, it is utilizing these concepts to make life more efficient. It's not just about dirtying the hands to be successful. It's about utilizing these tools to be more efficient, to be more productive. With this, I would end my session, and probably we will have any more details. Please contact me at any point in time. Thank you.